Alright, in this video, let's talk about the magnetic force on a wire. I'm going to assume that the wire is a straight section of the wire. So let's draw a wire, and we're going to be specific and say that we would like to calculate the magnetic force acting on that section of the wire indicated there. So that section of the wire has a length delta L, and the wire carries a current I. Of course, there wouldn't be any force on the wire if it wasn't in a magnetic field. So we're going to assume here that the magnetic field is B and it's pointing out of the page. Now, as you know, a wire that carries a current, well, the current is the flow of charges. So in that section of the wire that we're specifying with delta L, there's going to be some charges that are going to be moving. The total amount of charge inside that part of the wire, I'm going to call it delta Q. These charges are going to be moving with a velocity, which we talked in previous videos. That's the drift velocity. The charges inside a wire have a drift velocity. So every one of those, the total amount of charge delta Q moves with a velocity Vd. So we know that there is an equation that tells us what's the force acting on a charge that moves with a velocity in a magnetic field. It's called Lorentz Force, and the equation for the force is, let's put an arrow there. The equation for the force is that the magnetic force is delta Q times the velocity, which in this case is the drift velocity, cross product with the magnetic field. This is called the Lorentz Force. So what we would like to do though in this problem is to write the magnetic force acting on that segment of the wire as a function of the current in the wire and as a function of the length of the wire and also as a function of the magnetic field. That's what we like to do. Notice that the direction of that force is downwards. To figure that out, you need to do the cross product between V and B. So you can extend your hand, make your hand flat, put your thumb in the direction of the velocity. Your fingers should be sticking out of the computer screen, and when you do that, the palm will be pointing towards the bottom of the screen. So this is the direction of the magnetic force. Now, as I said, we want to use that Lorentz force, but we want to rewrite it in terms of the current and the length of the wire, of the section of the wire, and the magnetic field. That's the task that we need to accomplish right now. So we're going to start with this equation. Of course, the current flowing in a wire is equal to the amount of charge divided by the amount of time. So if you select a particular place in a wire, let's say this point over here, and you count in an amount of time delta t how much charge flows through that point, then the current would be the amount of charge divided by the amount of time. Now, the amount of charge inside that segment of the wire delta L, we're specifying that as delta Q, but we can write how much time does it take that amount of charge delta Q to cross that finish line that I indicated there. How much time would it take for all of that charge to move through that line right there? So notice that the first lines, or the first charges, sorry, that are going to cross are these guys, because they are right next to the finish line. So as soon as you start your stopwatch, they cross, and the last ones to cross the finish line are the charges that are towards the back, the charges that are a distance delta L away from the finish line. So those are the charges that is going to tell us how much time it's going to take for the whole charge to cross. They will cross at an amount of time t equals to delta t equals, well, the distance that they have to cover is delta L, and the velocity at which they cover that distance is the drift velocity. So the amount of time it takes them to go from the back to the front is delta L divided by Vd. So now we can stick that into the delta t in I equals delta Q or delta t. So we have now that the amount of charge or the current is the amount of charge divided by delta L divided by Vd, which we can rearrange as delta Q. The Vd in the denominator of the denominator goes to the top, And this is the equation that we have now. The current can be expressed as delta Q over delta L times the drift velocity. And we can rearrange this, multiply by delta L on both sides, to get that the current times delta L is equal to delta Q times the drift velocity. We're going to, since the drift velocity has a direction, and we're doing a cross product between the velocity, the drift velocity, and the magnetic field. So we're going to assume that the delta L is also a vector, and that it points in the direction of the current. That's the assumption that we're going to have from now on. So notice that now we're ready to write the magnetic force in terms of the current and delta L, because the term delta Q times Vd is now equal. We have just found that delta Q times Vd right here is equal to the current times delta L. So let's replace that. The current times delta L, cross product with the magnetic field. So this is the force on a straight section of a wire in a magnetic field when that wire carries a current I. Now let's do a quick application of this. So let's say that we have a region of space that has a magnetic field of 1 Tesla, and it is coming out of your computer screen. We're going to put a loop in that region of space, and that loop, as you can see, is a square loop, and the loop is going to carry a current I. The current is going to be 2 amps. The side of the loop, it's a square, so the side is going to be 0.2 meters. So we can figure out, or we would like to find out what is the force acting on each straight segment of this loop. Each side of the square is going to have a force acting on it. We'd like to figure out how much is that force. So the equation for the force acting on a wire is the current in the wire times delta L, the length of the wire as a vector, a cross product with the magnetic field. Remember that delta L is a vector that points in the same direction as the current flowing in the wire. So let's start with this part of the loop. So that wire is going to have a force, a magnetic force acting on it. To figure out the direction of the magnetic force, you can use your right hand rule. Again, your right hand, stretch your right hand, make it flat, put your thumb in the direction of delta L. Make sure that your other 4 fingers are pointing out of the computer screen. So when you do that, you'll end up with the palm of your hand facing right. See, so that will be the direction of the magnetic force acting on that segment of the loop. So that loop is going to have a magnetic force pointing that way. And we can calculate how much is the strength of the force, because the equation says that is the current times the length of the wire. So the current is 2 amps, the length of the wire is 0.2 meters, and the magnetic field is 1 Tesla. I don't worry here about the cross product, because delta L, the wire, is perpendicular to the magnetic field. So the cross product equation will give us a sine of the angle between the 2 vectors, but since the 2 vectors are perpendicular to each other, the sine of the angle is 1. So it's just the magnitude of the force is just the product of those 3 quantities: the current, the length of the wire, and the magnetic field. So 2 amps times 0.2 meters times 1 Tesla, that will give you a magnetic force of 0.4 newtons. So in the direction, we figure that it will be to the right. We can now look at the other section of this loop that has a current to the left, the same length as the other one, 0.2 meters. We can figure out what's the direction of the force acting on that section of the loop. So again, put your right hand flat, make sure that your thumb points in the direction of the current, make sure that your 4 fingers point out of the screen, because that's the direction of B, and you'll end up with the palm of your hand facing up the page or up your computer screen. So that's going to be the direction of the magnetic force. Okay, thumb to the left, fingers out of the screen, your palm is pointing up the page. So that's the direction of the magnetic force on that section of the loop. Same magnitude as before, 0.4 newtons, because it's the same length, and obviously it is the same current that you have everywhere in the loop. For that other two sections, you can practice using your right hand rule again, and you'll find that the force on the left section is to the left, and the force at the bottom part of the loop is downwards. Each one of those forces has a magnitude of 0.4 newtons. Notice how the magnetic forces are trying to stretch this loop. Now think about what would be the direction of those forces if we were to invert the direction of the current flowing in that loop. If instead of the current flowing counterclockwise, if we made the current clockwise, what would be the direction of those forces? All right, I'm going to leave it there. See you in the next video.